Okay, greetings from Poland once more, last day. All right, our learning objective for today is the following. We're going to describe phases as different organized lattices. We're going to define coordination number. We'll introduce some of the basic metal structures, BCC, FCC, simple cubic, HCP. We'll describe these later. We're going to establish relationships between the ionic radii, the lattice parameter, packing factor, linear density, and planar density. We'll introduce the HCP structure in some detail, and then we'll calculate the theoretical density of compounds if we have time. So let's recap what we've covered so far in this class. We started out talking about bonding, right? We then moved to chemical reactions, including thermodynamic driving forces, electrochemistry, equilibrium. Once we understood what equilibrium and how to understand that, we could talk about phase diagrams, which tells you what phases we find in equilibrium under what conditions, right? But something that we missed after we talked, obviously after that we talked about fracture, but something that we missed was this concept of what exactly are these crystal structures, right? We've been writing them as Greek letters, gamma, alpha, Fe3C, but up until now we have no idea what these crystal structures look like. Why are some of them soluble in one another, right? You can dissolve 2.14 weight % of carbon in this gamma phase, but not in this alpha phase. So what's different about alpha iron and gamma iron? Why is one so much better for dissolving carbon than the other, right? This chapter helps answer some of these questions because we geometrically look at how these crystal structures come together, right? Another point that we've talked about, if you remember our iron wire demo in class, where that piece of iron wire we heated up and it was drooping, but all of a sudden it shrunk a little bit and then it drooped again. That shrink was due to it switching from one crystal structure to another one. And the one at high temperatures is simply more compact. And so those atoms came together closer and that caused the wire to shrink, okay? So let's dive into crystalline materials. Crystalline materials are those that have long-range periodic order, right? So a lattice, we call this a lattice, in that the atoms sit in a specific spot and that's repeated in a specific way all the way through material in long range, okay? This order occurs spontaneously, right? You don't have to, like with a microscope and a really tiny set of tweezers, move atoms in these spots. It happens spontaneously, right? As you cool it from a liquid to a solid, they automatically do this, okay? Now, the 3D array of points where these atom positions are located, we call that a lattice. And within that lattice, there is a smallest repeating unit, which we call a unit cell, right? And this repeating unit is one that you can you can translate, moving side to side and up and down to fill all space. Just like wallpaper can fill whatever size wall you want, you can do the same thing with these unit cells in a lattice. So let's take this picture right here. In this picture, this sort of arrangement of dots, that could be considered a lattice because it could be used to fill all space, right? But what's the smallest unit cell? So next to your neighbor, take a sketch. What might be the smallest unit cell that you could repeat here? Okay, hopefully what you saw is this shape. This rhombus shape is the smallest unit cell that can be translated to fill all space. I know that some of you probably thought it was this triangle, right? You say, but the triangle's even smaller, right? And I can do this and fill it up. But you can only do that by rotating the triangle, right? The one next to it, like right here, that had to be rotated by 180 degrees and then translated. A unit cell is translate only, not rotate, just translate. Translate is moved side to side and up and down, okay? So that rhombus ticks the ticket because we can move it like that, we can move it over, we can move it down. That's our smallest unit cell, okay? So that's what a unit cell is. All right, let's dive into the metallic structures. Metallic structures, remember one thing about metallic bonding is it's not directional bonding, right? It's all these things they want to just share with all the metals around them. They share their electrons in the so-called sea of electrons. So because of that, because it's non-directional bonding, you get non-directional structures. These tend to be densely packed with a high coordination number. Coordination number is an important term to know. It is the number of neighboring atoms, right? So if you take an atom, let's go back over here, any one of these atoms, it's surrounded by how many nearest neighbors, right? If this is our atom, how many atoms are located at a equal but closest distance? You've got 1, 2, 3, 4, 5, 6. In that structure there, in that lattice, the coordination number is 6. Okay? Alright, so in metals, your coordination number tends to be a large number. You get high coordination. Okay? And so most of these metals can fit into a couple different classes: BCC, FCC, or HCP. We're going to describe each one of these in turn. Let's start with FCC. This stands for face-centered cubic, right? Face-centered cubic, that's metals like aluminum, silver, gold, copper, lots of other ones. Here's how you draw it. Draw your cubic lattice, right? It's a face-centered cubic, so we're going to start with a cubic lattice. So go ahead and draw this. You can draw your axes first if you want, in your X, Y, and Z directions. So here's X, there's Y, there's Z. We're going to draw our lattice now, right? Here's our unit cell, right? So you would place atoms where? You're going to place them at the cube corners, right there, 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 and there, right? So all at the cube corners, but you also place it, like the name suggests, face-centered cubic. You're going to place them at the centers of the face. So the front face, the back face, right face, left face, top face, bottom face. Like the fronts of, if this was a side, like a dice, those would be the centers of the faces, right? So in the face-centered cubic structure, that's where your atoms are located. Now, what do we know about metals? We know that they want to share electrons, so overall the atoms are all going to condense together until they're touching. So the way that I've drawn it, they're not touching, right? But we know that in a real atom, they're going to shrink, right? And we call that the hard sphere model, where you can treat them like they're spheres and then they touch. So let me ask you this. Turn to your neighbor and ask, where would these atoms touch? If you were to collapse them all together until they were touching, where would they be touching them? Along what directions? So TAs, go ahead and hit pause and discuss this. Okay, hopefully you realize that when you draw this as a cube, but you draw space filling with large atoms, right? When these things are large, I'm just going to draw the front face and not the other ones, but you see that they're going to be touching along the faces of the unit cell, right? They're touching along that line. Those 3 atoms are all touching along the diagonal of the face of this cubic unit cell. Okay, that's where they're going to be touching. Now, the next question is, what is the, let's see if we can talk about that. What would be the coordination number of atoms in this crystal structure, right? How many are they coordinated by, right? So in the FCC crystal structure, how many are they coordinated by? So again, on this one, you can just take a look at this atom for a minute. How many nearest neighbors does it have? Well, it's got 1, 2, 3, 4. Those are all equidistant. But then you could draw another unit cell next to it. Let's go ahead and do so. If we draw this unit cell next to it, then there would also be atoms on the front of that face, back of that face, and so we could draw how close it is to those ones. This and that, this and that. Those are equally close, right? And so we could also draw these atoms on the top there, on the bottom there. I'm going to switch colors just so you can kind of see this. But it's also equally close to that top, to that bottom, to that bottom. So I understand that's messy, but in 3 different directions, X, Y, and Z, it's equally close to 4 atoms. So the coordination number, Cn, is equal to 12. It is 12 coordinate. We told you that that's a high number, right? That's a large number of atoms to be equally close to. It forms a special geometric shape that we'll talk about a little bit later in this class. Okay? So that's the face-centered cubic crystal structure. Now, something that we should introduce is something called the lattice parameter. We talked about this previously. The lattice parameter describes the lattice separation distance. We call this A, right? So from the bottom of this unit cell down here to the top of that unit cell, that is 1 edge length of our cube. We're going to call that A our lattice parameter, right? So the lattice parameter A is a measure of the size of the lattice of the unit cell. So how about this one? We're going to do a clicker activity here, and the question is the following. If the lattice parameter of copper's FCC lattice is 3.601 angstroms, so that's A, what is the atomic radii in angstroms? So what I'm asking you is to relate, how do you relate this distance right here a radius of an atom to that A right there. So go ahead and give this your shot, and then we'll work through it together. Okay, hopefully you've given this an attempt, and you remembered first off that if you look along the face of an atom, that they touch along the face of this square. The edge of the square, that's A, but this distance here, if this is A, then that diagonal line across the face, you can use Pythagorean's theorem, and you want to remember that that's going to be equal to root 2 multiplied by A. And we remember that there was 4 atoms that touch along there, right? Here's 1, 2, 3, 4. There's 4 of those. So therefore we could write that root 2A equals 4 radii. Okay? So we can go ahead and plug this in, and we can solve for what our atomic radii should be. Radii should equal whatever root 2 times A is divided by 4. Okay, so if we go ahead and plug this in, I find that my radii is equal to 1.27 angstroms. Okay, so that is how the lattice parameter relates to the ionic radii in the FCC crystal structure. Okay, so next question that I have, the next clicker question is, how many atoms are located within the FCC unit cell? Okay, so go ahead and pause this and discuss. And the key thing to remember here before we put your answers in, take into account how many are actually totally inside versus only partly inside. Okay, hopefully you worked this one out. Let's go ahead and draw it. If we draw the crystal structure, remember we have atoms at the corners, and since those are at the corner, actually only 1/8 of the atom is inside. So there's 8 of those, and they're 1/8 of the way in. So 8 times 1/8, plus we've got the ones on the faces, top, bottom, front, back, left, and right. And since those are centered on the face of the cube, they're half in the cube and half out of the cube. So they're 1/2. So you're going to have 6, there's 6 sides to this, multiplied by a half each, right? Overall, this is equal to 4 atoms. So inside the unit cell, inside that cube volume, there's actually only 4 complete atoms, even though at first glance it looks like there's lots of atoms, okay? So something to note here is that the corner, right, the ones located on the corner and the atoms located on the faces are the exact same atom in the FCC crystal structure. And in fact, if we chose to place our origin at a different spot, it doesn't change the symmetry of our crystal. What am I talking about? So the origin, let's say the origin, we had it back here, maybe to start with, and this was X, and that was Y, and this was Z. Well, we just as easily could pick a different spot. Like, let's pick this one. Let's make this our origin, right? That would now be X, this would be Y, and that would be Z. It's no different, right? Let's see, the corner versus the face-centered atoms are the exact same atom in the crystal structure, okay, in the FCC unit cell. Just depends on where we place the origin. There's something called the atomic packing factor. The atomic packing factor is really just a measure of how compact the lattice is. Different crystal structures jam the atoms in there more than others. For example, remember our iron wire demo? At low temperatures, it was a less compact structure because at high temperatures, all of a sudden that same crystal structure shrunk together, so the atoms must have compacted. So we need a way to calculate how compacted things are, and we call that the atomic packing factor. We calculate it by taking the volume of the atoms that are inside the unit cell, and we divide it by the volume of the entire unit cell, right? So go ahead and for this one, next clicker activity is I want you to figure out what should be the atomic packing factor for face-centered cubic. Remember, we're treating atoms as spheres. Okay, go ahead and hit pause. All right, hopefully the TAs worked through this with you, and you remember that the volume of a sphere is equal to 4/3 pi r cubed. That's our volume of a sphere, right? And the volume of a cube, that's just equal to a cubed, okay? So in this case, what is the volume of the atoms? Well, remember that there's 4 atoms, so we're going to have 4 of these things, and they're each 4/3 pi r cubed. Okay, then we're going to divide that by the entire unit cell volume, which is a cubed. But we can actually make this a little bit better. We can simplify it, and we can remember that, oh, previously for FCC we had a relationship for lattice parameter and ionic radii, right? So we can write one in terms of the other. So let's go ahead and do so. Let's remember that A, let's rewrite this down here. We know that A can be rewritten as, where is it? A is equal to 4r divided by root 2. A is equal to 4 times the radius divided by root 2. So let's go ahead and plug that in right there. That allows us to rewrite this expression as 4 multiplied by 4/3 pi r cubed. This is then going to be divided by 4r cubed divided by root 2, right? So the 4's cancel. That cancels with that. Excuse me. Sorry. Let me go back. I need to fix this. We forgot to cube that whole thing. Right, that's A. We need to, but it's A cubed, so excuse me. This needs to be 4r over root 2, so I need to cube that whole thing. That lets this cancel, that cancels, and when you plug all of this in, you end up with 0.74, or in other words, 74% of the volume inside the cube is occupied by atoms. 74%. And this is interesting. This is actually, as I've got written here, that is the highest possible packing fraction for mono-sized spheres. Mono-sized means all the same size. So if you had marbles that were all the exact same size and you tried to pack them as carefully as you could into some sort of volume, you could never fill more than 74% of the volume with those spheres. There's always going to be 26%, which is unoccupied space. The only way to make that better than that is to take really small marbles and put them in the spots between your big marbles. And then you can make it a little bit better, but it's tricky to get much better packing. And you can't with a single size, okay? So there's some examples on how to calculate packing fraction on YouTube here. All right, we already talked about coordination number. Remember, it's 12, and the reason why is because if we go back to this, each atom, if you look at it, it is half of a face diagonal away from 12 different atoms. So its coordination number is 12. So we already did that one. What about body-centered cubic, right? So let's draw the crystal structure for body-centered cubic. This time it's slightly different. So let's start with our crystal structure. Let's go, again, it's cubic, so we can start by drawing a cube. The first thing we need to realize here is that we have atoms at the corners, just like before. Atoms are at the corners, but we've got one in the very center as well. One in the very center. And just like before, the way that I've drawn it right now is not touching, but in a real material, since these are metals, all of those atoms are going to shrink down until the hard sphere model, where they're touching one another. So go ahead and turn to your neighbor and say, where are they going to touch in this crystal structure? Okay, hopefully you realize that they're going to touch along what's called the body diagonal, right? So I'm going to redraw along the body diagonal here. Let me actually change color so it's easier to see. Along this diagonal, if that's that plane, I've sort of taken that slice out and moved it over, then we could say that this is the lattice parameter, and this is root 2 times the lattice parameter, since it's along, that's cutting the face diagonal. And then along the body diagonal is where they're touching. And again, we can use Pythagoras rule, Pythagoras theorem, and say that this is root 3 multiplied by a. Right, that's the distance there, and that's going to be 1, 2, 3, 4 radii. So it's almost the same as before. This time it's root 3 times a is going to be equal to 4 times r radii. Okay, so we figured out the lattice parameter relationship to the radii for body-centered cubic, and it's not that different from face-centered cubic. One was root 2a equals 4r, And in this case, since they touch along the body diagonal, it's going to be root 3a equals 4r. Okay. What do you think is the coordination number of atoms in body-centered cubic? So the next clicker question, what is the coordination number here? Okay, I hope that was easy to see that it's 8, right? You got this one in the center, and it's clearly equally close to these 8 atoms, and there's nothing else that we could draw that it's equally close to. So the coordination number is going to be equal to 8. What about the atomic packing factor? To figure out the atomic packing factor, remember that's the volume of the atoms divided by the total volume. So you need to figure out how many atoms there are. There's 8 on the corners, just like before, 8 times 1/8, plus there's 1 that's completely inside. So you've got 8 times 1/8, that's 1 plus 1. There's only 2 atoms per unit cell here. So let's go ahead and write this out. We've got 2 atoms per unit cell. We've got the volume of each one, 4/3 pi r cubed. We're going to divide this by a cubed, right? That's our lattice parameter volume. But we have an expression for a in terms of r right here. So let's go ahead and substitute that in. We're going to say that that's equal to 4r over root 3 cubed. The r's cancel out again. And now when we plug this in, we find that it's equal to 0.68, or in other words, 68%. So this is less densely packed than face-centered cubic. And this explains what we saw in the iron wire demo. The iron wire at room temperature is BCC ferrite. Ferrite is a BCC structure. It's body-centered cubic. And when you heat it up, when you heat that thing up, the wire started to droop, but then it transformed to the face-centered cubic, and when it did so, the atoms became more compact, so the wire shrunk again, and once the transformation was complete, then it continued to expand due to thermal expansion. So that's pretty cool. It went from 68% packed to a higher amount, 74% packed, and then upon cooling back down, it switched back to the more relaxed structure that's not quite as densely packed. Okay? All right, the last important type of crystal structure that I think we're going to get to is called hexagonal close packed. I think it's the last one we have time for. This one's different because it's no longer cubic. The other ones were easy. Drawing cubes is easy. This one's hexagonal, so it's a little bit trickier. To draw a hexagon, you have this length right here. That's A, the same as this one. That's also A. But that's different than this lattice parameter C. So for the first time, we have to have 2 different lattice parameters. We can't just have one to describe the volume of the unit cell. We need A and we need C, right? Now the top and bottom planes get a special name. This whole plane up here and this bottom one down here, those are called the basal planes, okay? The basal planes. Now the question is, what would be the coordination number for hexagonal close packed? What do you think it is here? So you can go ahead and pause the video and discuss what should be the coordination number. Okay, hopefully you had a chance to look at this. Let's just draw an atom. How about this one in the middle? Clearly it's equally close to 1, 2, 3, 4, 5, 6 along the basal plane. But these are also atoms, right? This one, that one, that one. And then there would be 3 in the next unit cell above it as well. So there's 6 in plane, 3 below, and 3 above. And if these atoms are all the exact same size atoms, then this atom is going to be sitting on top of these 3 and surrounded by these 6, and there'll be 3 more that sit on top of it. We're going to show you with tennis balls stacking how this looks probably when I get back. So we'll see maybe a better way to visualize this pretty soon. But the coordination number, since there's 6 in plane, 3 below, 3 above, the coordination number for this is also 12, just like FCC. Okay? Okay, the last thing that we're going to get to today is how to calculate theoretical density, right? So the density is super important for so many things in material science. We need to be able to calculate the theoretical density for these crystal structures, right? If I give you the lattice parameters A and C and I tell you what atoms are in here, could we go ahead and take a stab at calculating what the density should be? Sure, it's just mass over volume, right? So all you need to do is the following. Density is going to be Z. That's going to be the number of atoms or molecules per unit cell. So for metals, we're just going to do atoms, but soon we're going to get to ceramics and we'll have to talk about molecules. So for now, think atoms, that's okay. M sub W, that's our molecular weight of the atom, not the molecule. If you're doing molecule over here for Z, then you have to do molecular weight for the whole molecule, not for the atom. So again, we'll show you an example in a minute. V sub C is the unit cell volume, and N sub A is Avogadro's number, right? So let's go ahead and do this one. For which one did we do earlier? I think it was copper. So for copper, that's a simple one. It's cubic. We said it's cubic. It was FCC, so those atoms at the corners and along the faces. I think I'm missing one. Oh, the back one, right? So that means that there's 4 atoms per cell. That's equal to Z, right? So then density, oh, we also told you that the lattice parameter A was equal to 3.601 angstroms. So let's go ahead and plug this in. How can we calculate the theoretical density? It's going to be equal to Z times molecular weight. So 4 was Z for face centered cubic. The molecular weight of copper is, I've got it here, 63.546, 63.546 grams per mole of substance. Now we need to turn this into volume. So A, that's 3.601 angstroms. We're going to cube that to make it a volume. And then we would be done, except that look at the units. If we plug this in right now, we'd have units of grams per angstroms cubed. That's density, mass per volume. But we've got this mole. To get rid of that moles, we have to multiply it by Avogadro's number. So we're going to put in 6.023 times 10 to the 23rd per mole. And that's going to have the moles cancel out. When you plug this in, something to be aware of is that if you plug it in right now, you're going to end up in an answer with grams per angstrom cubed. So that's not the typical way that we report density. We typically report density in, density has units of grams per centimeter cubed, which happens to be the same as kilograms. Oh no, it's not the same. Never mind. It's another way that it's commonly presented is kilograms per meter cubed. They're not the same thing. So how do you make that conversion from angstroms cubed to centimeters cubed? The last thing I'll show you here before we wrap up is you just need to recall that, like, let's say that you're going from, let's say that you got your answer in grams per meter cubed because you converted angstroms to meters. How do you go from meter cubed to centimeter cubed? Just remember that, okay, if we're going to put 1 meter up here, and we want to turn that into centimeters, that there's 100 centimeters per meter, but this is meters cubed, not meters. So we need to cube this whole thing, which means this whole thing needs to get cubed when we do our conversion. So we will pick up here next time when I'm back in the United States, and we'll finish talking about crystal structures for the rest of this chapter.